Hello and welcome to the lesson on parametric and vector equations. So what's our goal today? By the end of the note and the homework, I want you to understand how vectors can be written in parametric and vector form. And you can demonstrate the skill by taking information I give you and create a parametric and vector equation. So that's the goals for today. All right, the note in front of you. To determine the equation of a line, what do you need to know? And right away I see at least 5 hands up in your home. Okay, what do you need to know? Well, from grade 9, everyone remembers that if I have a point and a slope, I've got everything I need. Point and slope. All right, and I still see hands up, which are great. That means that these people also know that in order to find the equation of a line, you just need 2 points. So either or. If you have a point and a slope, or you have 2 points, what are you going to do to find that equation? So off to the side here, your slope equation. Everyone still has that ingrained in their memory, I'm sure. y2 minus y1 over x2 minus x1. And then for those that had me in grade 9, I always taught the formula to look like this. And that's the transformed equation of a line. So if you had any of that information, you could jump, if you had number 1, you jump right into this equation, okay, because you have a slope and a point. If you had 2 points, you had to find slope first, and then use one of the points to do that. So there you go. So in grade 9, we know that slope defines the direction of a line's travel. So it tells you how far to go over and up. In grade 12, we changed the word slope. So we're going to change this terminology on you. I am now giving you grown-up speak now. So we don't talk about slope anymore. We talk about the direction vector. So that is our new terminology. So slope, m, equals small d. So slope equals direction vector. So we're not going to use the word slope other than this lesson hardly anymore. So slope equals direction vector. So there you go. And what's the reason for that? So a quick explanation for you. So if I, off to the side here, some musings. Okay, in grade 9, I taught you that if you had a point A, let's say, and you went 1, 2, 3 over, 1, 2 up, using the slope, you were using your rise and run to get your resulting line. Now, I'll do vectors in green. What you're going to be given is, here's the point A, that the line goes through, and it goes in that direction. So the direction vector is centered at the origin, so that the computer knows that that direction vector, okay, tells you what direction to go from the given point. So that's what we're doing. We're transforming it from what you did in grade 9, and I'm moving you to the grade 12 system. So, and you're going to find the transition's fairly smooth. So the first example right here, find the direction vector for each line. So first of all, I have to convince you that I'm not making this stuff up. So I'm going to use the slope equation first. So this is your grade 9, x2 minus x1. And it's going to be a little squishy here. y2 minus y1, so negative 7 take away negative 5 over 3 take away 4. My slope would be negative 7 plus 5, so we'd have negative 2 on top, 3 take away 4, negative 1, and I'm going to leave it in that form. Therefore, slope equals negative 2 over negative 1. So there's grade 9 for you. So grade 9. Now, moving you into grade 12. I'm going to tell you the direction vector is just vector AB. Can you solve this or find AB? I sure hope so, because we talked about it previously. It's just point B, subtract point A. And again, I'm going to do all the steps here. So that means that, sorry, some magic pen started. Point B is 3, negative 7, minus point A is 4, negative 5. The result when you subtract 2 points is a vector. So 3 take away 4 is negative 1. Negative 7 take away negative 5 is negative 2. And oh, look at that. Surprise, surprise. If you look at the similarities, here's your rise. Well, we know rise is just our y component here. And run is always on the x-axis. So it's our x component. So there's your relationship. Okay, rise over run. Your direction vector, so you can put this in, is just run, comma, rise. Pretty nifty, eh? And I find this equation, a lot people make less mistakes doing this process than they do doing this process. So there you go. So answer to B then. What happens if line L2 has a slope of 4/5? So now I'm telling you, here's your slope 4/5. What's the direction vector? Well, it's just in the form run rise, so 5, 4. And there's your final answer there. So being able to convert from slope to direction vector is done right there. Okay, moving along. So example of general form of a vector equation. So I want to come up with a vector equation, and I'm going to show you how it's derived using an example, something that you can follow through and understand the connection. So I'm going to create myself an offset Cartesian plane. Didn't work out just right perfect for me. And what we're going to do is we set it up x, y. I'm going to have a direction vector over here. I'm going to have some point P. So this is the given point. And what I'm going to say is point P naught, subscript P naught, is any point on the line. So D, it's our direction vector. Direction vector. P, point on line. So that's the given information. And P naught is any point online. All right. So off to the side here, I've got it covered up. Just some hints here. So P naught P, so that means this vector here is a scalar multiple of our direction vector. So P naught P is some multiple of our scalar vector. So what that means is that P naught P dot vector is some scalar multiple of the direction vector, and T is any real number, so it's just a multiplier. Okay, moving down further, what we want to do is we're going to write P naught P as a linear combination using the origin. So we've done this already. Here's our starting point. We want to end up here, and I want to use this point here. So that means it would be vector P naught O. O stands for origin, plus OP, and that's still equal to a scalar multiple of our direction vector. So I'm just writing it as a linear combination. And the resulting equation is what we call the general form. So let's clean this up a little bit. All right. So what is P naught P? I already told you that it is a point on the line. So it's a given point. So I'm going to use the subscript here. Best way to do it. Actually, I think I've given it the example. So right there. So we know what P naught is. So P naught P and P naught O is, and I guess we're going to take an interlude here. So I'm going to actually calculate this out, and we'll continue down below. So P minus P naught. So that means you'd have P is point XY minus -3, 5. So again, point P is any point on this particular line. Okay. So we end up with the vector x plus 3 and y minus 5. So that's what P naught P is equal to. But I didn't want that. That was a silly mistake. Sorry, because we don't want that. I want actually P naught O. My mistake. So P naught O is equal to the origin minus P naught. So 0, 0, -3, 5, which would give me a vector of 3 and -5. So that's P naught P taken care of. The vector OP would be P minus O. P is XY minus our origin, 0, 0. So we would end up with the vector X, Y. All right. So from that, oops, a little too far. I'm going to take that equation from up above. If you have room, I'm just going to start working down here with our information. So I'm just going to rewrite it. So P naught O plus the vector OP equals T direction vector. I now know that PO is the vector 3, -5 plus vector OP is just XY. So I'm just doing the substitution for the stuff I just solved up above. And what I want to do, I want to solve for XY. I want to get XY isolated. So XY equals the negative of 3, -5 plus TD, or finally putting it, -3, +5 plus T times our direction vector. All right, so what's the connection here? So there's the final answer for us. So there's the final answer for that question we were working on. Again, I just did the substitution from above for these two values. And now I want to take a look. Where did -3, 5 come from? So when you look back at the original question, -3, 5 is actually the point. So the first value here, this is the value of a point on the line. And this is our direction vector. So that's the explanation as to how we come up with the general vector equation. So on the next slide here, or in your note, you'll see I have a general form. So here's our our vector equation. And you're probably going to end up putting this on the cheat sheet just to keep them straight. And what you'll find over time, you're going to you have this memorized. It's also known as general form. You'll find I bounce back and forth with the terminology. So any line is defined by xy. So it's kind of like y equals my point AB plus t times the direction vector, where point P is defined as AB and T is an element of real numbers. So there we go. And I'm going to show you some examples on that. Really, if you know any point, then you're able to solve for any general equation. And then just to finish this up, actually in the next video I'll pick it up here and move through. So there's your general equation. We'll stop there and I'll finish this up in the next video.